Alright guys, let's start the lecture. Okay, so in previous lecture we talked about the topic of controllability and observability. And for controllability, okay, if the system we have here is this one here, represented by the system matrix G and H, then the necessary and sufficient condition for controllability is basically is this matrix. The rank of this matrix needs to be full rank, which is n. Okay, is the order of the system. Okay. Observability, and we're using a simplified version, considering all the control input 0, and just looking at this one here. As I mentioned, the definition is basically whether we can reconstruct the initial condition based on the observations of y of k, right, and k equal to 0, 1, 2, okay, over a certain period of time. If we can, then the system is said to be observable, right? Okay, so now let's take a look at what will be the necessary and the sufficient condition for this observability of the system, and then we'll finish this one here, and then we'll go to the next topic, which is pole placement. Okay, yeah. Okay, so I'll start from here, and basically we're gonna, based on the system, consider this one, x of k plus 1 equal to g of x of k. Okay, so from this x of k plus 1 equal to g x of k, okay, from here. Okay, now if you do this iteratively, basically let's say if we're trying to solve this system, this difference equation in here, the solution, as we know that this is basically g to the power of k x of 0, right? And the solution is this. Okay, and y, right? The output y is equal to c x of k. So then c times that. Okay, so this is your y here. So now you see we have a connection between y and x of 0. Okay. Alright, so observability basically saying is, okay, given y of 0, okay, those are your measurements, y of 1 and y of 2, okay, and so the question is, will we be able to reconstruct this initial condition x1 of 0, x2 of 0, and up to xn of 0, right? So that's the question here. Okay, so let's use the first n values of this y of k. So let's do this. Basically, I'll choose y of 0. Okay, when k equal to 0, what do we have? Cg x of 0. Okay, then we choose y of 1. Okay, Cg. Sorry, when k equal to 0, this is just a c here, right? When k equal to 1, is Cg at here. Okay, and then up to n and here, so c g n minus 1 x of 0. Okay, so you see we have a number of equations at here. So actually looks like there are n number of equations at this stage, right? Yeah, but if you remember, we'll say the output y, okay, can have m number of outputs here. Okay, so this vector, it's a n by 1 vector. Okay, suppose that to be n by 1. If this is n by 1, and each one of these n by 1, and there are how many of n by 1? There are n number of up to n minus 1. There are n number of n by 1 here, right? So totally, this is how much? What's the size here? It's n times m, right? So this is basically n times m number of equations. Okay. Yeah. So what's the idea? The idea is to given the left side at here, given the left side, to obtain the x of 0, right? To obtain x of 0 here. Okay. So it's like basically in terms of, if we say is in terms of the vector here, you have y of 0 at here up to y of n minus 1, and then you have this cg up to cg n to the minus 1 here, and then x of 0, right? That's this case. So given the left side, try to compute the right side, the x of 0. Okay? Yeah. So apparently, what you need to do is you can take the inverse of this matrix, or whether you can have enough number of equations to get a solution for x of 0, right? Yeah. So apparently, the idea here is this matrix, right? This matrix here, the rank of this matrix has to be full rank, right? Yeah, in order to solve for this x of n, because xn is n by 1 vector. Okay, yeah. So that's basically the idea. Now we said that basically the necessary and sufficient condition, okay, for observability, okay, is rank, okay, this matrix Cg up to Cg n minus 1, okay, this guy equal to n, okay, is this. That's your observability. Okay, so you have your system matrix G, you have your C. Okay, try to form a vector like this or matrix like this. Okay, and then look at the rank. Okay, yeah, and then you'll get the conclusion. Equivalently, okay, rank of this matrix, rank of A equal to the rank of what? A transpose, right? Yeah. So you can basically take the transpose of this one here, then the equivalent condition is, you can see it's check the rank is check this. What's the transpose of this matrix? It's a C transpose, right? Transpose this is transpose each one of the elements. Okay, and the transpose Cg is G transpose C transpose, and up to Gn minus 1 transpose and C transpose. Okay, yeah. So we need this guy to be n. Okay, it's the same idea. Okay, yeah. Yeah, the previous lecture, I don't know, there was sound for the first 5 minutes, and then all of a sudden the sound just gone. So we'll see if this time's okay, right? So that's observability. Okay, so the idea of observability is very simple. Or checking it is quite simple. Okay, in MATLAB it's called command obsv. Okay, so plug in the GC matrix. Okay, and you will be able to get the results. Okay, let's say you return to a certain variable. Okay, it tells you whether it's observable or not. Okay. Or alternatively, you can construct yourself a matrix like this. Then you use the MATLAB command rank, okay, to check what's the rank of the matrix. Okay. If it's n, it's observable. Okay. Okay. So that's the concept of controllability and observability. Right? Any questions? Okay. So now let's go to a different topic, a new topic, pole placement. In the Wednesday, the lab tour, and I mentioned about how easy it is to implement a pole placement controller, right? Yeah. Now, this is basically the idea of pole placement. Okay, so we're going to do the pole placement using state space model. Okay. And we're going to use a single input, single output system for a demonstration. Okay. Yeah. Of course, we're dealing with the linear time invariant system. So here is the system. Okay, yeah. Okay, so there, in terms of control, okay, right now the stage that we wanted to deal with, the control is this thing here. So here's your system, and then there is this so-called probably a problem is let's say temporarily we can call that maybe I can call it disturbance. Okay, and the disturbance is in the condition. Let's say. Okay. Remember in the lab, and I was twisting it a little bit, right? And then trying to go back to its original position. So, the amount of twisting basically initially give a different initial position x of 0, right? And that x of 0, let's consider the disturbance. And our objective, right? And our objective is to, we want our x of k to go back to 0. Okay? Yeah. So that's a simple objective. We don't want it to stay at that disturbance, and also we don't want it to just randomly wandering off or oscillating, right, without knowing where it goes. Okay. So if we wanted to go back to the system, then what happens is we have to construct a closed loop here. Basically, the U, the control input, right, yeah, has to be based on a certain feedback of the system. Okay, so then we can control the system, right? So how do we feed it back then? Right. So in this particular case, we're going to feed it back like this case here. So multiply by a gain k. Okay. Yeah. And then now, as you can see, basically the design parameter, right? Or basically the question is how fast do you want your x of k to go back to 0, right? It's going to be depends on the choice of k. Okay, right? So the k at here is your design parameter. Okay, yeah. Of course, you can also see if the discrete system comes from a continuous system. If it's discretized, it's comes from by discretizing continuous system. Then the choice of sampling time actually also affects the response of this x of k. Okay, how fast go back to 0. Okay. So now let's look at some of the details that are here. Okay. So by doing this, right? So what do we end up with then? So your u of k equal to this. Then let's substitute this one, okay, back into the original state space equation, right? Yeah. But before we do that, I can draw a diagram. So our system here is this. Here's H block. Okay. Okay. Let's use here is a Z minus 1 and here. Here's G block. Okay. If it's just an open loop, okay, for this one system, this is the open loop here. Okay. And this is your U of k here. Okay. And those are positive. Okay. And here it's your x of k. Okay. So that's your diagram. This is a diagram representing this one here. I mean, if you want to use a MATLAB to build the system, right? You can just basically use this one here. So let's say if it makes sense, and I say this is x of k, and there's a delay. So before this delay, this is what this is x of k plus 1, right? It's x of k plus 1. Okay. Yeah. So you look at the x of k plus 1. What does this signal at this location equal to? It equals to this one plus this one here, right? These two. Okay. And the signal at here is x of k times g. See, right? X k times g. And signal at here is h times u. So basically, that represents the single input, single output system here, right? And now, given this simple objective here and a simple idea of controller design, so what we're doing is we're basically feeding back this x of k at here, okay, and then times this negative k, and coming back here, right? Yeah. So if you recall that the block that showed you in the experiment, all we did is basically this whole chunk, right? This whole chunk is the system. Okay. So if it's a practical system, you don't need to worry about it. It's already there, the block, right? And all you need to build is this guy. And of course, we need to pick a proper key here, right? Yeah, to get our desired response. Okay. Now, if you do simulation, then you need to build this block here, right? If you do simulation. Okay. Yeah. Okay. So now let's do this. Let's plug this expression back into this state space state equation at here. So what do we end up with? Okay, so we end up this guy here, right? This. This is basically a difference equation. Okay, a difference equation. Now it's like a difference equation. There's no control input here, right? There's no control input basically. And if you use difference equation, so what's the solution now? Is that right? Yeah, that's the solution, right? Yeah. Okay, so now the question is back to the objective. The objective is given certain initial condition or certain initial disturbance. What do we want? We want this guy to go back to 0, right? To go back to 0. Okay, yeah. So if it's like a differential, first order differential equation, you know, if a y at here, and the solution of that is equal to a at t, okay, negative y to the power of at. Okay, so if I want the y to go back to 0, okay, and there's a certain initial conditions to C imposed at here, and that a value has to be, let's say this guy here, if the y has to go back to 0, this e has to be exponentially decay function, right? So the a has to be less than 0. Okay. In other words, you know, the pole has to be in the what side of the S equation? Right or left? In continuous system, left, right? Yeah. So same thing at here now. If forget about this matrix here, let's see if I consider just a constant a times the power of k. So what could make this a to the power of k go back to 0? The a value has to be what? As k goes bigger and bigger, you want this one to go back to 0. The a has to be negative, just a negative, -3, less than 1, -3 is less than 1 too, right? What does a has to be? Negative, less than -1. So how about negative 0.5? What's the value of a negative 0.5 to the power of k as k goes to infinite? Does it go back to 0? Yeah, right. But can it be less than -1? Basically, the question is. It can, right? Yeah. So in other words, the a value has to be within where? A unit circle, right? Yeah. Okay. So this is not a constant, but this is a matrix, right? This is a matrix here. So the idea is, what can make the power of a matrix go back to 0? See what I'm saying, right? Yeah. So you have a matrix to the power of k. So in other words, when you multiply the matrix by k number of times, and the whole matrix is supposed to go back to 0. Okay? Yeah, all the elements should go back to 0. Yeah. So what makes that? What condition will make that happen then? Right? Yeah. And the condition to make that happen is the eigenvalue of this matrix, okay, the eigenvalue of the matrix needs to be within this unit circle. Okay, so that's basically the idea. Is that good? Yeah. So what we want is, right, the eigenvalue of this G minus HK, okay, needs to be within the unit circle. Okay? Yeah. So remember, what is the design parameter? Design parameter is the K, right? It's the K here. Now, if I don't have the K, the original system, right? The original system is just a system matrix G. So then, if you don't have this K here, if we only look at the original system G at here, you know, that's basically the system matrix. Whatever the eigenvalue of the system matrix G, that's essentially the pole of the system, right? There's no control of that. Okay, it could be stable, could be not, right? Yeah. But now you do have a choice. Now you can design your K such that to make this G minus HK's eigenvalue of the pole to be within the unit circle, right? Yeah. So in other words, what we can do is we can do it to reversely. Let's say maybe I can choose a certain, okay, low pole locations, for example. Okay, maybe I can choose a desired locations the poles. Okay, because as we learn, the location of the poles really determines how fast the system responds. Okay, right? Say for example, you know, you have a 0.5 to the power of k, and you have a 0.1 to the power of k. Guess which one goes back to 0 quickly? 0.1, right? Yeah. So that's the idea. Okay, if you choose your location 0.1, you'll have faster response than 0.5. Okay, yeah. So we can choose the post location here, and eigenvalue of this guy here essentially comes out of the determinant, right? If you set the determinant, okay, if you set the determinant to be 0, okay, then you can solve for these eigenvalues, okay, or the poles of the system, right? Yeah. Then the determinant of this guy here, okay, ultimately it's gonna give you, okay, a polynomial. Okay, it's a polynomial out of this determinant. The polynomial of the determinant, let's say this is the poles that you decided to use, right? This is the poles decided to use. Then the polynomial that you're gonna have is basically z minus lambda 1, z minus lambda 2, and z minus lambda n. Okay. This computer is super busy at here. Not sure what it's doing. Okay, yeah. So basically, this guy right here is going to be this so-called your desired, okay, characteristic equation. Okay, this is going to be your desired characteristic equation based on your desired pole location. All right, yeah, pole location. So it's like what you're doing here is we're selecting the poles of the system, or we are placing the pole of the closed loop system at the desired location. So this is basically pole placement, right? Yeah. We need to come up with a proper key value such that the poles at here, 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 here. Okay. Yeah. So the theory basically at here is, okay, the necessary and the sufficient condition for arbitrary pole placement. is that the system is completely controllable. Okay, yeah, it's basically the controllability condition of the system. It's a theorem. So the first step is you always to check what is the controllability of the system, right? And then if it's completely controllable, then we can use this pole placement, okay, as free as we want. So let's take a look at the example, okay? Okay. We'll use a simple system here for illustration. So let's say I have a system which is a double integrator. Okay. Here's a system, a double integrator right here. Okay. It's essentially you have like a y of z, u over u of z, that kind of case, right? Input, output. Okay. So it's quite actually commonly saying second order system, even for a simple mechanical system. For a simple mechanical system, your torque equal to G, times theta double dot. Okay, right? Yeah. That's second order system. So let's say we're gonna do down a pole placement for the system in here. Okay, and we're gonna use a discrete digital controller for design. So the first step from here is you need to change this double integrator into a discrete state space equation. Okay, so that's the first step. And to do this, right, if you recall that there are different ways of doing this, right? I think I'm not going to go over all the details, but there is an appendix for this lecture in terms of a derivation of this discretized appendix. So you have this appendix, okay? Yeah, and basically, I think I have gone through similar structures in the lecture. But for example, based on this system here, your y of t equal to u of t. Okay, it's a double integrator, right? It's a double integrator here. Okay, so what do? We go from here to construct the continuous state space equation model first, right? So we need to choose the state variables first. Okay, so let's say my first state variable is chosen as the position of the system, and then my second state variable is chosen to be as the velocity of the system. Okay, yeah. So now you can construct your continuous state space model now based on the choice of your state variables, right? Yeah. Your continuous model, okay, is going to be 0, 1, 0, 0, okay, x of t, okay, plus 0, 1, okay, u of t, okay, like this. And then right from here, so what do? In one of the lecture, we discretize the system, right? Discretize the continuous state space model. So basically, if this is A and this is B, you have the formula for discretization, right? You'll be able to get the discrete state space model. And this one turned out to be, okay, x of k plus 1 equal to 1 t 0 1 x of k t squared over 2 t, okay, u of k. Okay, so that's the state space, discrete state space model for this second order double integrator. Okay. Okay, so now let's do this. We're gonna pick, let's say, well, let the K matrix equal to K1 and K2. That's our gain matrix, right? And what we have is we're gonna use this one here to do a feedback. Okay, to do the feedback. And in other words, this is going to be negative K1 x1 of K minus K2, okay, x2 of K. Right? Yeah. So small k here. Alright, yeah. So then let's see what happens then. If I plug this U, okay, back into here, okay, plug the U back into here, okay, then you do all the basically multiplications and the simplifications set it here. So in other words, it's the same expression as we had at the top of this is G minus H capital K and then X of K, right? It's this. So plugging the K here, you have the H. So in this case here, this is the G, and this is the H, right? Yeah, this is G, this is H. Okay. So you have all the parameters here. So we plug it in here. So we will end up with, okay, 1 minus K1 T squared over 2, T minus K2 T squared over 2. Negative K1T, 1 minus K2T, and X of K. Okay, so that's your G minus HK, right? That's your G minus HK. It's a 2 by 2 matrix. Okay, yeah, so it's not too bad. And so what we want is we want to check, right? We want to see where is the poles of this or eigenvalues of this 2 by 2 matrix. So in other words, we look at the characteristics, okay, of this matrix. Okay, so we look at the eigenvalues of this matrix. So calculate the determinant, right, of this guy here, Zi minus this matrix. Okay, yeah. So set equal to 0. And now you can do that. Actually, not too bad. It's a 2 by 2. So you'll end up with this expression, this polynomial. So z squared plus k1 t squared over 2 plus k2t minus 2 z plus k1 t squared over 2 minus k2t plus 1. Okay, you'll end up with this polynomial here. Okay, yeah. So K1, K2, right? They are the gain matrix. They are the design parameter. You will choose the K1, K2, or calculate the K1, K2, such that the characteristics that are here give you the desired poles, right? Yeah. So now here's comes the question here now. So let's say lambda 1, lambda 2, right? Lambda and lambda 2 are the desired one. Okay? They are the desired poles. Okay? If they are the desired poles, then what's the desired polynomial? This is the desired polynomial, right? Okay? And I can expand this one here, so it's going to be probably z squared plus p1z plus p2 equal to 0, right? So this is your desired, okay, polynomial or characteristic equation. Okay. This is the desired. This is the actual, right? This is the actual ones with a design parameter k1, k2. So guess what? So P1, P2, those are known, right? Okay, those are known here. You compare the coefficient of these two. So really what we want to do is we want to let the K1t squared over 2 plus K2t minus 2, this guy here equal to P1, right? And this guy here equal to P2. Okay, yeah. So you got two equations and two unknowns. Then you solve for this K1 and K2. And so the K1 in the end equal to 1 over T squared 1 plus P1 P2. And K2 and equal to 1 over 2T 3 plus P1 minus P2. Okay. So basically when you design your controller, which is the feedback over here, that K, right, really depends on the value of P1 and P2, or ultimately depends on lambda 1 and lambda 2. So apparently the P1 equal to negative lambda 1 plus lambda 2, and P2 equal to lambda 1 lambda 2, right? Yeah. Okay. Yeah. Yeah. You have this the continuous system block AB at here, right? The G matrix, if I remember correctly, it's e to the power of a times the sampling time, right? And the H is the integral e to the power of a lambda d lambda, then times the what? Times the b, something like that, right? Yeah. Okay. So anyway, the formula. One assignment that you for this second one here. Okay, so that's the idea of pole placement. Actually, that's the idea of pole placement for a pretty simple system like a second order. You can always hand calculate to get the desired K1 and K2. Alright? Yeah. Okay, so let's look at another example right here. So this one is more of a more of design. So basically, we will have some design specification. Okay, then yeah, we'll have some design specification here. Then we'll pick our poles according to our design specification. All right. So here's my new plant. Okay. This is a plant very similar to the plant that you're going to deal with that Quanser the setup there, okay, second order. Okay. Yeah. So you're going to have a slightly different key value, at the gain value at here, other than 10. You have a certain time constant here, but they're all going to be second order, just like this guy here. Okay. Yeah. So let's say this is the transfer function, right? It's transfer function of the system. Okay. So then apparently, what's going to be the differential equation of the system? It's going to be y of t for this one here, and y of t here equal to 10, okay, u of t, right? Yeah, like this. Yeah. So then, just like the previous example, okay, you choose your state variables. As we always do, our first one is position, and second one is the velocity. Okay. Yeah. Okay. Yeah. So this is where one thing I would recommend that you got to be careful is you can use MATLAB. You plunge in the numerator denominator for the continuous system. You can use MATLAB to convert it to a state space model, right? But the state variables of the conversion using a function not necessarily going to be position velocity. Okay, so what I would always recommend to do is you do this basically manually by picking the state variables like this. Okay, so you know what you're dealing with. Oh yes. Good. Okay. Okay, so you'll be able to construct the continuous state space model and use the formula. You can discretize to get the discrete state space model, right? Yeah. So let's say we're going to discretize this using a sampling time of 0.1, right? So then if you calculate it carefully, then you should end up with this this result. Okay, so my lecture kept a little more decimal numbers than this guy here. So here I'm using 3 decimal numbers. Okay, so that's your discrete model. So then we're going to design our system, okay, pole placement based on this discretized state space model. Okay, yeah, so we're going to design this. Same as previous example, our U, or the control input, right, is negative k, x of k. Okay, so your parameter basically is k1 and k2. Okay, x1, x2 of k. Okay. Yeah. The closed loop, the closed loop system matrix is G minus HK. Okay, it's G minus HK. Okay. Then the characteristic equation, okay, is this ZI minus G minus HK. Okay, yeah. So same idea, is just a bit of some more numbers got involved here, right? Some more numbers. Okay. Yeah. So anyway, you're gonna end up with this long expression in here: z squared plus 0.48 K1 plus 0.952 K2 1.905 Z plus 0.04847 K1 K2. Okay, yeah, I gotta end up with this long expression in terms of the K1 and the K2. Okay, design parameters. Okay, so let's say now what you're saying is I'll just arbitrarily, give certain values for K1 and K2. So let's say you set K1 equal to 1 and K2 equal to 0. Okay, so you're just trying to errors to see, does that give me what kind of response does that give us, right? Yeah. So plug in the K1, K2 at here, and your polynomial of this guy will end up with this. Okay, we'll end up with this. Okay, yeah. Okay, so the question is, now you look at this one here. What's the pole of this equation? Also, what's the root, right, of this polynomial at here? Okay, and that location of the root or the pole really determines the response of the system. So this second order system is quite easy. You can solve that, right? You'll see that the solution of this one is actually a pair of conjugate roots. Okay, the solution. So Z, there are 2 roots. Okay, they're not real. They are a pair of the conjugate ones, and the value of this is this. So that's the pair. When you have whenever you have a conjugate, and whenever you have a complex number, just a quick reminder, the complex number can always be written as a magnitude and what? The argument, right? Yeah. Okay. So you have basically, if this is the complex number here, this is r and this is theta. Alright? Yeah. You can always write the complex number like that. Okay. So in this case here, this is the r, right, and this is the theta here. Okay, this is the theta. Okay. Yeah. Now, the location of the pole, okay, or the value of r and theta. So let's see, by looking at r here first, is that r less than 1? Apparently yes, right? Yeah. So basically, the pole location is within where? Within the unit circle, huh? Yeah. But you look at the r here, it's pretty close to where? To the boundary, right? To the boundary. Okay. And we know that as we were learning, the closer, as we said, and if you look at the real axis, maybe I use the example 0.5 and 0.1. So basically, the closer to the origin, they're supposed to have a what? A faster response, right? Yeah. So the r and the theta really determines a lot of very important parameters in your continuous system. If you remember, we generally have this second order system here for illustration of this several important continuous system concept. So what are they? They are, what's the settling time, right? What is the overshoot? What is the rising time? Okay. What about the damping ratio? See, right? Yeah. So same thing. Even though you're discretizing, you have a continuous pole here. After discretization, right? And you always have a mapping, basically, which is what we're going to learn in the next lecture. You always have a mapping from the continuous system poles to the discrete domain time, discrete time domain poles. Okay, so from the S poles to the Z poles, there's always a connection, and that connection, okay, is this: Z equal to e to the power of TS. Actually, we've had this already, right? Remember that? Yeah. When you sample the system as impulse system, it's impulse sampling. That's a connection between the S and the Z. Okay. Yeah. So essentially, the idea is right now you can get this. Given the r and the theta, then I can roughly know what is the damping ratio, right, corresponding to a continuous system response. Okay. The formula, okay, given some discrete derivations, you will see that the damping ratio corresponding to the roots, okay, related to the r is this, and theta. Okay. So that's connection between r theta and the damping ratio zeta. All right. Yeah. So we'll derive this. Otherwise, you'll have the formula. Okay. So don't worry. Okay. So that's damping ratio. So if I plug in the r and the theta, okay, into this formula here, so this is damping ratio. Okay. So what do we get for the zeta? So we get the zeta to be 0.46. Okay, 0.46. Okay. And similarly, you can also derive is what would be the time constant? Okay, given this pair of poles, what's the corresponding time constant concept in a continuous system? Okay, yeah, and that tau, okay, can be derived as this. So T over ln R. Okay, sampling time over ln R. So if you plug in the T at 0.1, plug in the R, this is going to be 2.12 seconds. Okay, 0.12 seconds. Okay. So basically, you pick the key one. This is what this is based on the key 1 equal to 1, key 2 equal to 0, right? It's a pretty wild guess. You actually end up with somehow okay values. Okay. Yeah. But now, if the user saying is looking at the results, no, I don't think this is good enough. Let's say that's okay, but this one is a bit of too long. Okay, right? Maybe I should have a shorter time constant. So let's say my tau desired, really I want is 1 second. Okay, it's 1 second. Then what would you do, right? So you're gonna have to go back to redesign your K1, K2, right? To come up with the desired a better R and a theta. That's the idea, right? Yeah. So now let's do this. So basically, you have this is known now, and this is known, and then we can calculate what would be the R, right, corresponding to the desired time constant. So that basically means ln R equal to negative t over tau. Okay. So t is 0.1, and tau is 1 second. So this is a negative 0.1. Then R will be 0.905. Okay. So different now, right? So previously 0.954, right? Yeah, 4. And we also need for the theta. So what do? We come back here. We said we said the damping ratio is okay, but actually this is not that okay of in time. 0.5. You probably want a 0.7, something like that. Okay. But anyway, so if this is your really desired damping ratio, and R is this guy here now, so we can solve for the theta now, right? We can solve for the theta now. Okay. Yeah. So the theta square can be solved, which is this expression. Okay, so your theta is going to be this guy. Alright, yeah. There we go. So this is basically based on the desired pole and desired based on the desired time constant and desired damping ratio, you get the desired pole location. This is in terms R and theta, right? Yeah. So then, what's the desired pole location? It's lambda 1, 2 equal to R times positive and negative theta. So 0.905 positive and negative 193 readings. Okay? Yeah. So plug into your computer or calculator. Okay. Make sure this is readings, right? If you calculated if you're calculating your cosine, your computer can calculate in terms of degree and the readings. So make sure they are on the readings. So you end up with your pole location as this. Okay. So that's your desired pole location, okay, which is different from the first set of a pole location, right? Yeah. So if this is the desired pole location, then what's the desired polynomial, like characteristic equation, which is what? Z minus lambda 1, z minus lambda 2 equal to 0, right? Yeah. So plug it into here, okay, and you get z squared minus 1776z plus 0.81. Yeah. So this is your desired, basically, characteristic equation. Okay, yeah. So we're almost there now. So here's the desired polynomial here. And what is the actual polynomial of giving the feedback? Where is it? Here, right? See, this is the actual polynomial giving the feedback considered K1, K2. So you set this whole chunk equal to that coefficient, and this chunk here equal to the other coefficients, right? Yeah. And then solve for K1 and K2. Okay? Yeah. So you'll be able to solve to get K1 equal to this, and K2 equal to this. Okay? So that's a simple demonstration of designing the pole placement schemes, right? K1 and K2 based on certain desired criteria from the user. Okay. Yeah. So different guys will have a different different ideas here, right? So look at the MATLAB code, okay, for simulation in here for this example. Okay, the computer is really busy doing things here. Show you what how the response looks like. Response, what's going on here? Okay, so I just want to show the simulation results, that the figure. It's taking a bit of time here. It's awfully slow. Okay, so let's wait until the PDF file is open here. Okay, so any questions on the idea of the pole placement now? Yeah? Is that good? Okay. Okay, so now let's continue it here. Okay. We'll look at, oh, here we go. We'll look at some other concept, okay, in terms of this pole placement. So here's the results basically, okay, based on the pole placement design here. I give it, so check out the code, okay, yourself. So I give it initial condition here, and then you have the simulations, right? Yeah. The bottom here is actually not time. It's steps basically. So like up to this stage here, for example, like 20 steps, right? Yeah. So if you want a time, you need to time the bottom here by 0.1, the sampling time, right? Yeah. So for example, here it's going to be 2 seconds here, right? Yeah. So time constant is what? Time constant is basically the time it takes to reach 63% of this desired location, right? Yeah. If you go from here to here to 63%, so that's about somewhere, you see somewhere like this, right? At 10 times 1 is 1. So essentially, this is a verification whether you have your design satisfied or not. Okay, that makes sense? Yeah. Okay, so let's continue from here. Okay, that's the pole placement. And now let's look at another thing here, which actually will help you in terms of understanding the pole placement, also doing the pole placement design. So what we're looking for is solution through the control canonical form. Okay, so remember when we derive the state space model, right, based on the Z pulse transfer function, we emphasized on two pretty important formats. One is control canonical, the other is the observable canonical, right? Yeah. So what's the idea of the control canonical here? So basically, here's the idea now. You can use that very easily for pole placement. So y of z over u of z. Okay. This is a generic polynomial that we have been using. Okay, and the control canonical based on this polynomial, right? So we're talking about the state equation right here. So the control canonical for the G matrix, right, based on this polynomial, this pulse transfer function, is this. And then negative A1. So there should be another row here. So that's your G, okay? And this is the G matrix in the control canonical format. And H is 0, 0 up to 1. Okay. Yeah. So that's the G here. The characteristic, if I only just look at the G matrix here, and we look at the characteristic equation, okay, so basically look at the determinant of the Zi minus G. Because this is special format, okay, because it's special format, you can easily see that the polynomial for this one is this. Okay, this is the polynomial. So the coefficients, right, for this polynomial A1, and that's essentially the coefficients of the numerator there, okay, a denominator. Okay, yeah. And what do we want again? We want to design a pole placement, right? Pole placement. So basically, we want to design is our gain matrix K, right? Let's say we set it to Kn minus 1 and then K1, right? So n number of Ks. Okay, yeah. Okay, so if the G is in that kind of a format, then we're looking at is the new matrix now, G minus HK, right? G minus HK. So this new matrix G minus HK, okay, if you plug it in, it's like this. very, very similar, okay, to that G matrix, except the last column. Okay, except the last column, the last row. So the last row here, negative an minus k plus kn. Then negative an minus 1 plus kn minus 1. Okay, and then up to negative a1 plus k1. That's your G minus HK matrix. Okay, so if you compare these two matrices, okay, the only difference is the last row. Okay, yeah, and we said, you know, you can verify that z, the polynomial for this z I minus g is this, right? Is this, and then guess what? What's the polynomial or characteristic equation for? What will be this characteristic equation for this guy here? You know, use the same idea. Instead of coefficient here is a1 to an, its coefficient going to be this, right? Okay, yeah. So okay, so that's your desired characteristic equation. Okay, yeah. So this is based on a control canonical form. So what do we do now? We select k1 up to kn, right? That's what we're doing. Okay, and we select k1 up to kn based on what? Based on the desired polynomial or desired pole location. So if you have your desired pole location, so let's say, then you will be able to construct the desired characteristic equation. Right? So let's just say your desired one, okay, is this. If this is the desired one here, okay, and where does it from? You know, where is it from? It is from a set of desired poles, basically, right? Here's your actual. Here's your desired. So look at that. Guess what? It's so easy to calculate the k1 up to kn, right? So basically, which means your ki equal to alpha I minus ai, and I is 1, 2, up to n. Okay. And that's the advantage, right? That's the advantage when the system matrix G is in the control canonical format. Then you can easily obtain your k's, the gain, feedback k gain, right? Based on a set of desired pole location of polynomial. Okay, yeah. Okay. Okay, so then the question here is, you probably should say is, okay, so if this G is so good, and you know, polynomial, I can get this from here. But what if, right? What if the what if this G matrix, okay, initially it's not in the control canonical format, right? You know, it's pretty possible, right? If you design using MATLAB or using this true picking the state model, the approach that we did, right? Not necessarily the G will be in the control canonical format. Okay? So if it is not in the control canonical form, then the question is, can we put that into the control canonical form, right? Yeah. If we can, then it's beautiful. So then we can basically calculate this guy here. Okay. Yeah. So I'm not going into detail. This is basically sort of optional here. There are a set of linear algebras involved here, but you can definitely convert, right? You can transform the G, okay, into the control canonical. So how do we do that? So I'll just roughly tell you what to do. You pick this basically similarity transformation approach. It's the idea. So you do the similarity transform. So you like this T inverse GT similarity transform to transform that into the control canonical form. Okay? Yeah. So the whole question is, what will be the transformation matrix T, okay, to give us this control canonical form, right? Yeah. The T should be designed as this. It's T is equal to a multiplication of two matrices. Okay. The first matrix M is this. This is your first matrix M. So, can you tell me what this matrix is? Right? And this one, no, this one. This matrix. What this mean? Where this matrix? Where did you see this again? Yeah, controllability, right? Yeah. And the W, okay, is a little bit okay, weird question, but weird matrix, but it does have certain patterns. A minus 1, A minus 2, and A1 1, and then A minus 2, A minus 3, and 1 0, up to A1 1 0 0, 1 0 0 0. Okay, that's your W. So where's the A1 AN minus 1 from? You know, that's basically from our the trans function at here, right? Yeah, at here. Okay. Yeah. So if you want to use the formula, you're gonna have to stick to that the notation, the conventional notations we used in that post-trans function. All right. Yeah. So if you do this, you will be able to transform the G matrix into a control canonical form, and then you can use that idea, right? Yeah, for pole placement. Okay. Any questions? Yeah. Okay. So last bullet points, okay, is so-called Ackermann formula. So that's another way of solving for the K. Ackermann's formula. So it's double N and here. Okay. We're not going to prove this one here now. The proof of this one you can find. You can see the proof is on page 409 on the textbook. Okay. But we'll just put down the formula here. Okay. Yeah. Here is the system equation. Then let's see, desired pose is this. Okay, desired pose this. Okay. So you will be able to, based on the desired pose, you will be able to construct the desired characteristic equation, right? As we did. So let's just say after construction, okay, you end up with a desired polynomial for the characteristic equation. Okay, is this guy. Okay. Then the Ackermann's formula is the following one. Okay, the K, so basically the gain matrix K, okay, is equal to 0, 0, 0, 1, okay, a vector times h gh gn minus 1h inverse, okay, inverse, and times alpha c g, okay, alpha c g. Okay, that's the Ackermann formula. So my requirement for you is, okay, you need to be able to hand calculate some lower order systems. For example, second order one using this Ackermann formula. All right? Yeah. So what is alpha cg then? Right? Alpha cg is, see, this is alpha c. This is your desired polynomial here. Okay, desired polynomial. So alpha cg essentially means you replace the z with g. Okay, you replace the z with a g. Yeah, this semi needs to be a pretty long polynomial, but if it's second order, right, you don't have that many to calculate. Okay, yeah. Is that okay? Yeah. You can always verify using ACKER command in MATLAB called Ackermann formula. So that command will return the k by giving it, I think it's just GH, okay, yeah, and it'll be able to give you back the k, okay, yeah. Oh, there should be another p matrix. P represent is a vector, the location of desired pose. Okay, yeah. All right, yeah. There's another command called place. Okay, it's very similar usage of this. Okay, it's like a pole placement. Okay, but Ackermann's generally we use that for single input, single output, just the formula here. The command place you actually can also use on the multi-input, multi-output system. Right? Yeah. So, any questions? Oh, good. All right. So.